Your homework tonight. This is lesson 16. I told you you should at least do part 1. Some of you got to do it in class. I'm going to show you how to do part 2 as well. So part 1 says there are 4 samples of air being collected at each of 3 different locations. Each air sample is in a different size box. Assume that the temperature, 273 Kelvin, is at all 3 locations. So temperature is the same. Our volume is changing in certain conditions. This right here in mole represents in the number of particles. Remember that 1 mole is 6 times 10 to the 23rd particles. So this tells us 3 different conditions, like it said, or 3 different locations. We've got at sea level, Mount Denali, and then an airplane in flight, so even higher. Notice that the pressure goes from 1 to 0.5 to 0.25. So it says fill in the missing amount of moles of gas molecules for each box. So we see what happened to the volume. It looks like it increased by 11.2 for each situation. They made it that. So we have to look at what happens to the number of molecules in each of those volumes in each location. So first, the number of molecules doubles or increases by 0.5, 0.5. So it must increase by 0.5 in the next box. So that's moles. I write my units. I look over in the next box, or I can look at this row here to see what happens in each situation. As I see, the pressure goes from 1 to 0.5 to 0.25. It goes from 1 to 0.5 to 0.25, also for the number of particles. So it decreased by half, decreased by half. So I'm going to do the same thing for this first box here. 0.5 cut in half is 0.25, and then half of 25 is 12.5, so the decimal would be 0.125 mole. For this part, cut in half $1.50. Think of it that way. Half of $1.50 is 75 cents, so this is just math from here. Half of 0.5, 0.325 mole, or 0.325, sorry. Okay, half of 2 is 1 mole, half of 1 is 0.5 mole. And then it says describe at least 3 patterns that you notice in the data. So as the volume increases at a certain pressure, atmospheric pressure, what happens to the number of moles? Well, it gets increased, sorry. As you go from sea level to Mount Denali, you could say, oh, well, I notice at the same volume, the number of particles gets cut in half. At the same volume, that happened here. The number of molecules got cut in half. Okay, so describe at least 3 patterns you notice in the data. You can just look at the data, the numbers, and what's being described in the box to figure that out. For number 3, analyze the data at sea level. It says, what is the number density in moles of gas molecules per liter of gas in the 22.4 box at sea level? So 22.4 liter box is here. And it says, at sea level, what was N over V? Well, here's N, the number of molecules, and the volume is given 22.4 liters. So it says I can give this in moles of gas molecules. So that's fine. 1 over 24, and then I use my calculator to figure out what the number density is. What is the number density of the gas in all 4 air samples at sea level? So I go to sea level, and I have to calculate N over V for each situation. I already did the 22.4 liter volume. I have to do the same thing for 33.6 liters, for 2 moles and 44.8 liters, and for 0.5 and 11.2. And what you're going to find is that the number density, N over V, is equal to a constant called K. That constant stays the same for the sea level situation. It's going to be the same for all volumes and all number of particles. At the Mount Denali situation, it's going to be the same for the airplane. Doesn't matter what the volume is, the number of particles is going to adjust so that N divided by V is constant. What is the number density for each location? You don't have to go through and calculate each volume now. You can just say, okay, I know for Mount Denali 1 mole divided by 44.8 is going to give me the number density there. I know that in a plane, I can calculate the number density by just choosing one number of particles with one volume, and I could do that. Explain why the pressure is higher at sea level than at Mount Denali. Well, what you have to do is look at the pressure, look at the number density, see how the number density compares. Okay, number 6. How many moles of gas would be in a 25-liter box at sea level? How are you going to find that? Look back, look at the patterns, or maybe you could calculate it. So in between 22 and 36 would be 25 liters. It'd be closer to the 24 end. So you can look at this to predict it would be between 1 and 1.5, or you could do an actual calculation. For part 2, number of mass, consider samples of different gases. Look, this is at STP. The drawings simply represent the number of gas particles in correct proportion to one another. Okay. In the box is showing helium gas. I find helium. Where is helium? So I look for helium. I find helium gases. It says, how many moles does each sphere represent? Okay. Which boxes has or have the most gas particles? So you'd look for the box with the most gas particles. Which boxes have the most total atoms? So here you have to distinguish between, like, for example, CO2, that's a molecule, but actual atoms are what? Individual elements. So you have to figure out which of these boxes actually has the most number of particles and the most number of atoms. And that depends on what the gas inside these boxes is. It says the masses of boxes 3 and 4 are different. Explain why. Okay, there's 3, there's 4. This helium weighs 4 grams. This nitrogen box weighs 28 grams. I want you guys to look at the periodic table for that. Compare the weights of helium and the weights of nitrogen. Number 6 says, describe or sketch a box containing 8 grams of helium atoms at 1 atmosphere. Show the relative number of helium atoms and the size of the box compared to the size of the boxes on the table. Okay, so you have to compare. Like if I had 6 grams of helium atoms, it would look this way. Count the number of helium atoms you see there. If I had 4 grams of helium atoms, it looks like this. Notice the number of moles for each of these boxes. When I have 6 grams, there's 1.5 moles. When I have 4 grams, there's 1 mole of helium. When I have half of that, 2 grams, there's 0.5 moles of helium. So if I look at, what it's asking me to do, sketch 8 grams of helium atoms in 1 atmosphere of pressure, what's going to happen? Well, I've got to adjust the number of moles. So you be careful about how you present that. For number 6, it says describe or sketch a box. Number 7. If you know that 2 gas samples are at the same temperature, what do you need to know in order to determine which gas is at a greater pressure? Okay, I want you to think about the definition of STP. I want you to think about one of the key points we made today in our notes. For number 8, consult the illustrations in part 2. At a temperature of 273 Kelvin and pressure of 1 atmosphere, STP, what volume does 1 mole of gas occupy? Does it matter what the gas is? Explain. Okay, so you guys need to think back to the definition of STP. I mean the definition of what happens with gases at STP. What volume do they occupy? Do all gases occupy at STP? And that question will be pretty easy. The second part, you have to think a little bit about. Anyway, this is your homework, part 1 and part 2.